I'm going to be talking about concavity and convexity. We've already discussed functions that are increasing and decreasing on certain intervals, but there's more than just that to the behavior of a function. For example, let me draw two functions next to each other that are both increasing. One of them like this, and one of them like that. Even though they're both increasing, they behave in very different ways. The first one is what we call a convex function, or concave up, and the second one is concave, or concave down. What it means for a function to be convex on an interval is that if we choose any 2 points on the graph, and we draw a line between them, then the function lies completely below that line along those x values. Similarly, a function is concave if for any 2 points on the interval, we draw a line between them and the function is above that line for all those x values. Another way of thinking about this is in terms of tangent lines. If we draw a tangent line between 2 points, or at 2 different points on a convex function, the one with the higher x value will have a higher slope. So the slopes of the tangent lines are increasing, or the derivative of the function is increasing. Similarly, for a concave function, the derivative is decreasing. However, because of what we already know about increasing and decreasing functions, we can say that if the second derivative of f is greater than 0, this implies that the first derivative is increasing, and this is exactly what it means for the function to be convex. Similarly, if the second derivative on this interval is less than 0 always, then the function is concave. Now one might ask what happens when the second derivative is 0. In that case, we sometimes get what's called an inflection point. If the graph of our function looks like this, notice that above a point around here, this function is convex. Let's call this point x0. However, below that point, it's concave for a while. In fact, we can tell that the derivative is increasing above x0 and decreasing below x0, which means that at x0 the second derivative is 0. So f double prime of x0 is equal to 0. And this is what's called an inflection point, when it changes from being concave to convex. However, it's not always the case that when the second derivative is 0 we have an inflection point. In fact, let's say we draw a tangent line at x0, and then we flip this function by reflecting it over the tangent line. Doing this doesn't change the upper half of the function, so the derivative will still approach, or the second derivative will still approach 0 around x0 from the right, and reflecting the left side still makes it approach 0 from the left. It's just positive there instead of negative. So here the function is always convex, however the second derivative is still 0 at x0. Now one useful application of convexity and concavity and using the second derivative is to tell whether local minima and maxima are minima or maxima. Let's say we have a function that looks like this. We can see by checking the first derivative that this point here is probably a local minimum or maximum based on the fact that the derivative is 0. But we don't know for sure, and we don't know which kind it would be just by looking at the first derivative. However, if we check the second derivative, and f double prime of x0 is less than 0, like it is in this picture, we'll know that the function at x0 must be concave, which means that it must be at a maximum. Similarly, at this point here, let's call it x1, we can see that it's at a minimum by checking the second derivative, since the second derivative will be larger than 0. So f double prime of x0 is less than 0, and f double prime of x1 is greater than 0. While this second derivative test works most of the time, there are still cases where the second derivative will be equal to 0, and you won't be able to tell whether it's a minimum, maximum, neither, and possibly an inflection point as well.